Before the final, will there be a review session or just the office hours?
There's the regular office hours, and as I say, I think to me the best illustration of what it is that we're trying to do are these various practice problems that I'm posting. And so, I mean, if you want to review materials, again, the central material is effectively kind of the first 5 chapters of the book. So the regular, statistical mechanics and partition functions, regular thermodynamic identities, in particular the definition of the free energy and so on. And then the one thing that was not covered in the midterm would be the quantum statistics, so problems with Bose-Einstein or Fermi-Dirac distributions. But as I say, if you want to ask more questions about this, I would really ask you to either dial in on Friday, this Friday, or the Friday after. Okay, we can talk more about that. Okie dokie. So, so the thing I wanted to do today primarily is to see how these correlation functions can be extended to finite time. And this, in some sense, really is something new, because so far, all of these thermodynamic averages that we've taken, they were always kind of static. I mean, we do something in thermal equilibrium where everything is sort of eternal, that, you measure the system truly is in thermal equilibrium. It doesn't matter whether you measure the pressure now or 5 years from now, it's always exactly the same. So the one excursion into time-dependent phenomena that we did was this excursion way at the beginning of the class when we studied the diffusion equation. And this will indeed become relevant again now. Okay. Now, I want to follow the notation of the book, where in order to introduce these ideas, the book now distinguishes between various kinds of averages that we can take. So one of them is, if you wish, the average that we've taken all along, that, we write these kind of brackets, and the average that we've taken all along, we will just now call that the equilibrium average. And what is meant by that is a standard indeed, you average things with the partition function. So it's an equilibrium, which really means in terms of the correlation function an equal time average. Okay. So, so what we want to generalize this to eventually is some kind of average where we somehow study many evolutions of the system where it's coupled to some kind of heat bath, so that we can determine a time-dependent correlation function. So this generalization, we will use the same kind of brackets, but we will use this symbol EV, which is just a general ensemble average of any kind of correlation function. So this is just the same kind of average, but generalized to non-equilibrium phenomena. Okay. And finally, the way we're going to get there is by forming an average where we study kind of a time evolution using something like the diffusion equation, which is a deterministic equation, but we average the diffusion equation over different initial conditions, where the initial conditions are drawn from the sort of standard equal time equilibrium ensemble. And so that kind of averaging, that will be denoted by a square bracket, where we average with respect to some kind of initial condition. Okay. So, and And so we're going to have to assume something about the time dependence, and I already sort of indicated what that is. So the problem we're trying to study is that we imagine that we have some kind of initial state. So in our case, there was some kind of density. So there was a mean density. Okay. And then you see fluctuations around that. And here I already draw them a little bit more smooth, something like this, okay? And we saw that if you measure the correlation function in the spatial direction, it's effectively just delta correlated, at least in the simplest non-ideal gas case. But now we want to explore how that evolves in time. And the idea is that the main thing that's happening here is that, okay, so you have a situation like the one that I just drew, where, you know, just randomly somewhere in space, you have an upward fluctuation of the density, okay? So if you have an upward fluctuation of the density at some time, that will, of course, kind of revert to the mean. But the number of particles is conserved. If you have an upward fluctuation of the density, the particles can't just disappear. They have to, if there's an overdensity somewhere, the only way that can revert to normal is if these particles kind of diffuse away. And so somehow we imagine that sometime later, this will look somehow more smooth because this overdensity has disappeared. Now, at the same time, of course, there could be some other fluctuation appearing somewhere else now. So that's, of course, perfectly possible. But for now, we'll just focus on this kind of idea that we imagine in our minds that there was some overdensity or underdensity somewhere, and we're somehow studying how that reverts to normal. Okay, so so indeed, the tool that I wish to use is the diffusion equation. So the idea is that the time evolution is just diffusion. So we have this kind of equation, and indeed we imagine that there was some kind of initial condition, and the way this initial condition will now evolve is by the regular diffusion equation. Okay. And what the book uses for this assumption is it calls it Onsage assumption, or the Onsage regression assumption. Okay. So what they mean by this is we already know that if we just pick an initial condition where indeed we, you know, you have a little bit of a fluid and you inject some overdensity or you inject some extra material, that will tend to spread by the diffusion equation. But now we generalize this to a case where this initial overdensity is not something that you did by adding something to the fluid, but something that happened randomly. And so really the only hypothesis here is that a random fluctuation evolves in time in just exactly the same way that that a sort of explicit fluctuation that you impose on the system would evolve. And okay, that actually sounds incredibly innocent. That doesn't even sound like much of an assumption. But there are indeed systems where that can be more complicated. Okay, so what we want to study now is we want to study what that means for the correlation function. So a correlation function, which is now a function of time, that again is some kind of average where we now take this density rho of RT, okay, with some initial condition, some rho I, minus the mean density, okay, correlated with, oops, this kind of bracket, okay, correlated with the density at some different time. So the simple situation is we can take a correlation function between a density at time and space 0 and some later time and some different spatial position. So the second one could just be rho of 0, 0. Okay. So this is a correlation function we can study. Okay. So so a priori, there's not clear how we should proceed, but given that we now have an equation for the time dependence, we could try to derive an equation for the time dependence of this correlation function. So you could compute d by dt of c of r and t, okay? And then on the right-hand side, of course, the d by dt, there's only one term that it can act on, which is this term in the first bracket. Okay. And everything else is the same. Okay. And now, of course, we just insert this equation of motion. So we insert the diffusion equation. So we use this result in here. And so then what we would get is that this is d times n squared of rho of r and t with some initial condition. And again, the second half is all unchanged. Okay. But now, again, this gradient in the diffusion equation, there's only one term in the whole expression that actually does depend on position. And so you can just pull this out of the whole average. Okay. And once you pull it out, it's just the initial correlation function. Okay. So effectively, what this shows is that the correlation function satisfies exactly the same kind of diffusion equation that the density itself satisfies. Okay, so we conclude that d by dt minus but we also know what the corresponding initial condition is, because the initial condition is the correlation function at time equals 0. And that's just the equal time correlation function that we computed earlier. So the initial condition that goes with this is that c of r comma 0 is just this delta function. Okay. So, so what we would like is some kind of function. So this correlation function is a function that satisfies the diffusion equation in time, and it has an initial condition that's just a delta function in space. Okay. And so now I know that was a long time ago, but if you try to remember the beginning of the course, kind of before Corona and everything, we actually already introduced this function. And this function was just a green function for the diffusion equation. So this c of r and t is just up to this factor. So the green function is defined with the delta function as an initial condition. And here it's a delta function multiplied by kt over alpha. But up to this factor, this is just the green function. And so we can just go back to the beginning of the course or the beginning of the book and just look it up. And so this function is then C of R and T. So you remember that the way we constructed the green function is by a more or less standard trick, which is that you take the diffusion equation and you Fourier transform it so that the gradient squared just becomes a factor of k squared in the Fourier transform. Then you can solve the delta function. If you Fourier transform, it just becomes a 1. So in Fourier space, the green function for diffusion is just 1 over k squared, and then you Fourier transform back. So, so this green function, again, there's an overall factor kvt over alpha, and then the green function that we found was 4 pi et to the 3/2 times an exponential factor, which is minus r squared over 4 dt. Okay. And the way we talked about this earlier is that this exponential factor effectively describes the spreading in space. So that exponential factor described the fact that the mean r squared, if you have some kind of blob that diffuses, goes as, you know, the square root of d times t. So that's a kind of hallmark of diffusion. Sorry, it goes like dt. So the root of this goes like root dt. Okay, so this is the hallmark of diffusion, that kind of the mean, the root mean square distance goes as the square root of time. Okay, so so if you have some kind of initial condition, so previously, again, the only difference is that originally our diffusions were, you know, our sort of inhomogeneities were man-made, but now our inhomogeneities are just kind of random. So, so if you have any kind of initial fluctuation that has some given widths that starts to spread in time, you know, it slowly spreads out. And that width is, again, it goes as square root of, so there's some width to this delta r, and that will go as root dt. Okay. And the other question is you can ask is, if you have some kind of local overdensity, you can ask how that, if you just sit at the centroid of this local overdensity, how does it decay in time? So previously that was space. Now we can look at the time dependence. So in time, any kind of overdensity will decay as 1 over t to the 3/2. And again, that comes from this pre-exponential factor in the correlation function. And so what is interesting about this, that so even though the equal time correlation function, at least in an ideal gas, it was kind of trivial, it was just purely a delta function. If the dynamics is described by diffusion, the unequal time correlation function actually is kind of non-trivial. It has real time and spatial dependence. And this, by the way, effectively, of course, if you make the time very small, this does eventually become just a representation of the delta function. So if you take this function of r and t and you make t less and less, then of course the distribution becomes narrower and narrower, so that the initial condition really is a delta function. Okay. So so this was indeed, it was just an average over, you know, random initial conditions, and in a random initial condition, indeed, the only correlation was this kind of delta function-like correlation. But we can also come to a more systematic treatment of the case where indeed you do try to impose on the system a sort of given initial condition. And one way to study that is called linear response. Okay. And so here the idea is, so we're studying some kind of thermodynamic variable again, that could be the density, or it could be the magnetization of the system. And in linear response, we imagine that we couple this thermodynamic variable so we have some kind of thermodynamic variable. So this could be, we will just call that S, but that could be something like the density, or it could be the magnetization, okay? And we couple that to an external force. Okay. So, so first of all, what do we mean by this? So it means that there's some kind of free energy that describes the system. So there's some kind of F, and this will now be split into the free energy without the coupling to this external field and some kind of coupling to a force. Okay. And so what does that coupling look like? Well, by linear response, what is meant is that the coupling is just purely linear. So there's your thermodynamic variable, this S of x and t, and it couples to some kind of force, F of x and t. Okay. And it's the fact that this F appears linearly that gives the name linear response to this. Okay. So why are we allowed to assume it's linear? Well, in general, of course, it will be more complicated, but if the external force is sufficiently small, then again, you can take any free energy that depends on some kind of external force, and you can just Taylor expand it out, and then the first term will always be linear. So no matter how complicated the real coupling is, we think that there will always be some kind of limit in which the coupling is linear. And indeed, many of the practical examples are precisely of this type anyway, where some of the dominant term is predominantly indeed kind of a linear coupling. So, so for example, imagine that the thermodynamic variable that you're interested in is indeed the density of some kind of gas, or the density of the fluid. And so how could we try to locally modulate the density? Well, in mechanics, they could just be moving in some kind of external potential that you impose on the system, some kind of external harmonic oscillator sort of potential. And then this coupling would simply be, you know, the density of the particles couples to some kind of external potential. Okay. And that indeed, you know, in quantum mechanics, that coupling, if you look at the Schrödinger equation, is exactly linear. Or in classical mechanics, again, that coupling is exactly linear, that you have some density of particles moving in external potential. The contribution to the free energy is just a contribution to the energy, and that would be exactly linear in the external potential. Or if, for example, again, your system is some kind of Ising magnet, and your thermodynamic variable is the magnetization, and now we do what we did before, so we just couple this to an external magnetic field, then the coupling of the magnetization to the external magnetic field in ordinary electrodynamics, you know, if you don't have a very complicated nonlinear medium, it's just exactly linear. So you'd have a term that's just the magnetization of the system times the external field. So, so the thing that you can now study, you know, and indeed many experiments are precisely like that anyway, is that you have the system sitting there in thermal equilibrium, and now you start to play with this external field. So, you know, you probe a magnet by having a time or spatially dependent magnetic field, or you probe a fluid by letting it move in some potential, and you try to to externally manipulate that potential and see how the density of the fluid changes in response to that. Okay. So the question you ask is always just how does the medium respond? Okay. So what you're asking is, you have this this thermodynamic variable that we call, say, S of x and t. Again, that could be something like the density. And you want to say how that responds to some kind of external force. Okay. Now, in general, in order to determine that, you will have to solve some complicated set of equations and average them over thermal, initial conditions and thermal equilibrium and so on. But given that the free energy is exactly linear in this external force, we would imagine that at least at first order, you can also just Taylor expand this thermodynamic variable. And at leading order, the response would also just be exactly linear in that force. Now, we think it's exactly linear, but again, it doesn't have to be completely local, because if you somehow impose, again, you make a potential that imposes a local overdensity, again, the system will start to diffuse out. And so the response could be linear in the external force, but not necessarily local, okay? So the way we allow for that is that the response is an integral over all possible positions where I may have applied that force and over all possible times at which I may have applied that external force. But of course, the integral over time is only this, the response is presumably causal. So the system may respond to any kind of force that you applied in the past, but certainly not to a force that you apply in the future. So the upper limit of this time integral is plus t, but it goes all the way back to minus infinity. Okay, but in principle, you could have applied that force anywhere in space, and the density changed because the overdensity kind of diffused out. Okay, so then the most general kind of response is that there's some kind of function, and that function is usually denoted by a Greek chi, that depends on how far away you applied the force and how long ago. Okay. So this magic function is some kind of response function. It's called the response function. Okay. And as I mentioned, the fact that we take this upper limit to t is what guarantees that things are causal. Okay. And again, linear response is the assumption that the response of the thermodynamic variable is still just linear in f. So, if f is not small, then in general, there could be extra terms that have higher powers in f in them. But if the force is sufficiently small, we would imagine that the leading order behavior is described by something that's just linear in f. Okay. So, so what can we do with this? So number one, just to simplify the notation a little bit, again, in this integral over time, the time integral was taken from minus infinity to plus t. You can effectively incorporate that in the response function so that you write something like this, that you have a response function that depended on the space difference and a time difference, but the time difference was meant to be such that we only focus, it was t minus t prime, where t prime is always less than t. So effectively, we focused on positive time arguments, and that ensured that we're only looking at truly causal things, so that there was a force applied in the past, and then the system somehow responds in the future. So we believe that this whole thing should always be proportional to a theta function in time. Okay. So once you somehow explicitly take care of this theta function, it's somehow safe to take the expression for the linear response and use a time integral that goes all the way from -infinity to +infinity. So that has the advantage that now you can write S of x and t as an integral over all of space and all of time. Okay. And why is that useful? It's useful because this relation, in some ways, is more natural to look at it in Fourier space. And that may be something that, again, you sort of remember from doing Fourier transforms in other fields of physics. So what I've written there on the right-hand side is, it's some kind of integral where you multiply two functions. But you see that the kind of function multiplication that occurs is a convolution integral, where somehow one function is taken at x prime t prime, and then the other function is taken at x minus x prime t minus t prime. And what you may remember from E&M and other lectures is that when you Fourier transform a convolution integral in Fourier space, that just becomes ordinary multiplication. And so you can just go through all the Fourier transforming to convince yourself of that, but I will just use that. So if I take the whole thing and I Fourier transform, then S of x and t becomes some kind of function of k and omega. So I will use a tilde to denote Fourier transforms. And so this is just the product of the Fourier transform of the response and the Fourier transform of the force. And the Fourier transforms are defined in the usual way. So it is S tilde of k and omega is an integral over dx and an integral over dt. Okay, and the other Fourier transforms are defined in the same way. Okay, and again, the tilde just denotes the fact that I Fourier transformed it. So I just denote the Fourier transform of S of x and t by S tilde of k and omega. And here again, for simplicity, I'm just following the notation that the textbook employs. And so effectively, as I mentioned, what I've used here is that if you have a convolution integral, and then you Fourier transform, that becomes an ordinary product. Okay. So, so the original thing up here okay, that was a convolution. And then after Fourier transforming, it just becomes an ordinary product. Okay, so so what that somehow suggests is that this Fourier transform of the response function, that's somehow an interesting object to look at. Okay. So this Fourier transform, again, it's simply defined by k omega, it's an integral over time, an integral over space. Okay. Now, so the original response function was just an ordinary real function because it was the response of an ordinary real thermodynamic variable, something like the density or the magnetization, to an ordinary real force, either a mechanical potential, some kind of external magnetic field, and so on. So this chi of x and t, that was an ordinary real function. But if you Fourier transform it, I mean, you multiply it by each of the ikx and so on. So that's a complex function. Okay. So, so by looking at this in Fourier space, this function suddenly has a real part and an imaginary part. So in general, it's somewhat true that this chi tilde of k and omega, that now has a real part, which for strange historical reasons is called chi prime, and an imaginary part, which for strange historical reasons is called chi double prime. So there's a factor I there. So this is the real part. And this is the imaginary part. And again, these primes, the thing that's sometimes confusing is, it's just notation. It's not a derivative. So, and again, and the same for chi double prime, obviously. And again, it just so happens that there was a very influential publication where somehow this whole idea of looking at the response function in Fourier space, and then studying the real and imaginary parts, where that was somehow explained in great detail. And for whatever reason, that paper used this funny notation of writing it as chi prime plus I times chi double prime. And that paper was just so influential that the notation somehow stuck. And since the notation can now be found in so many publications, even textbooks, who maybe decide that this is really kind of unfortunate that was called chi prime, they can't really change it. So somehow we're stuck with this funny notation of the chi prime and the chi double prime. And again, the important thing to remember is just not to mistake it for taking derivatives. It's just a name for the real part and the imaginary part. I mean, frankly, personally, I find it more useful to indeed, in order not to confuse myself, to just write instead of chi prime. We can, of course, always just write. It's the real part of chi tilde, and chi double prime is the imaginary part of chi tilde. Okay. So one of the things that's amusing about this is that these functions now have certain symmetries. Okay. So so chi in Fourier space is a complex function, but the complexity only comes from that Fourier factor. So if, for example, you take the complex conjugate of chi, then all you're doing is you're flipping, you're complex conjugating the Fourier factor, but the Fourier factor is e to the ikx minus omega t. So complex conjugating that just flips the sign of the I. So it's actually the same as flipping the sign of k and omega. Okay. So again, this is just a complex conjugate. Okay, but there's actually a little bit more here too, which is that if you, so now we have to assume a little bit about the structure of the system. So if you have a system that just has regular parity invariance, so that so it doesn't matter whether you apply a force at plus x and study the response at plus x, or you apply a force at minus x, study the response at minus x. So if you have any kind of system with parity invariance, so that the original response function is even in x. So if you have parity invariance, so that chi of x and t is the same as chi of minus x and t. Okay, then you can see that the response function is actually also then even in k, because if you flip k, you can always undo it by flipping x, but if the real response was even in x, then that doesn't do anything. So this would mean that chi of k and omega is the same as chi of minus k and omega. But then that means that this complex conjugation in principle flips k and omega, but since the system is invariant under k goes to minus k, then what that would imply is that the only thing that you need to flip is just omega. So if that is indeed the case, then chi star of k and omega is the same as chi of minus k and minus omega, which is the same as chi of k and minus omega. Okay. So, so if I now decompose chi into a real part and a complex part, so if I write chi is, chi prime plus I times chi double prime, then under complex conjugation, of course, the real part stays the same and the imaginary part flips. So then chi star is chi prime minus, okay. Now, chi prime and chi double prime are themselves summa functions of k and omega, okay. So, so what that means is chi double prime, since it's odd under complex conjugation, it must also be an odd function in omega. And chi prime, since it's even under complex conjugation, it must be an even function in omega. So what I mean by even and odd in omega is simply that chi double prime of minus omega must be minus chi double prime of omega, okay. Because otherwise we cannot satisfy this relation, okay. So what is the purpose of this long spiel? Number one, I mean, it actually depends a little bit. I don't know how much of that you do in electrodynamics, but if indeed you studied in electrodynamics the dielectric function in some detail, the dielectric function in general is also a function of x and t. The dielectric function is indeed sort of one of these response functions. It tells you how the polarization of the system responds to an external electric field. So you may or may not have studied the complex properties of the dielectric constant, which is exactly the same as the the symmetries of this generalized response function. So one thing that this does sort of makes contact with response functions that you see in other fields. Okay, but what it also does, it makes it more transparent what the physical meaning of this kind of chi prime and chi double prime is. Okay, and so the way one can establish the physical meaning is one of the things that you can look at when you couple the system to an external force is you can ask how much work that external force is doing on the system. So you can study the power dissipated, which is the same as the amount of work done. And the amount of work done on the system is just the usual sort of mechanics expression. So we have some kind of external force, and then we have some kind of thermodynamic variable. So the work done on the system, if S actually is position and F is an ordinary force, and the work done would just be the integral of F ds, okay? We just generalize this to more general situations. So it could be magnetization times field or density times potential. And you can integrate that over time just by using that this is F ds by dt times dt. Okay, so this would then be the amount of work done per unit time. And since we live in Fourier space, it's somehow easiest to just consider a purely harmonic force, and then using Fourier transforms, you can always just generalize this to any kind of time dependence. So you can consider a harmonic force. Okay, so you write f of t is some kind of Fourier component f omega times e to the I omega t, say. Okay. So you can now go ahead and try to compute the amount of work done by a harmonic force. And so where does the susceptibility come into this? Well, the susceptibility comes in because we will, of course, use that, S of k and omega is just chi of k and omega times f of omega in this case here, if we just not make it a function of k. Okay. So this again is effectively just a little exercise in doing Fourier transforms. And I don't know, I didn't want to go into super great detail. The calculation is done in the textbook. Again, it's just an exercise in doing Fourier transforms. And so what you find is that the power dissipated, so which is a function of omega, is omega over 2. It's the Fourier component of this work function squared. And of course, it must be related to the susceptibility. But again, that's the place where you can use symmetries of the susceptibility. And it turns out that the only thing you need is the part that's odd in omega. And the part that's odd in omega is the imaginary part. Okay. So, so what this exercise somewhat demonstrates is that the imaginary part of the response is somehow related to dissipation. And in some ways, we actually did something similar sort of last year when we just considered ordinary driven harmonic oscillators, where you have some kind of pendulum or, you know, just a massive body attached to a spring, and you just harmonically drive the suspension of the system. And there's a similar question that you can ask, which is how much energy are you actually putting into the oscillator when you do that? And again, that's actually easiest solved by taking the corresponding differential equation. You write it for an external harmonic force, and then you just solve that equation by Fourier transforming it. Then it becomes a purely algebraic equation. And that's how we got this kind of resonance behavior for a driven harmonic oscillator. And once you solve the equation, you can again ask yourself, this external force, in principle, it can do work on the system. So it can pump more energy into the system. And that, again, is also proportional to the imaginary part of that response function. So this kind of result is actually a very general kind of result. It appears in ordinary classical mechanics. It appears in electrodynamics. And again, it's just a general statement in thermodynamics that if you compute the imaginary part of the response function, that tells you how much energy an external perturbation is actually pumping into the system. The thing that's sort of different in a thermodynamic system is if you do that in classical mechanics and you have a driven harmonic oscillator and you're pumping energy into the system, then at the level where you're studying the equation, you're just increasing the amplitude of the pendulum. You're sort of increasing it without bound, actually. So the only way that indeed you can stabilize it is if you also add some amount of friction to the system. And so then what the friction would do is indeed eventually heat the system. And in a thermodynamic system, you effectively always assume that this will be the case, that this power dissipated, that just thermalizes. And so the imaginary part of the response function then determines how much heating you're doing on the system. So if you're applying an external magnetic field or you're applying external potential to some kind of fluid and then you're harmonically driving it, then the system will absorb some amount of energy and convert that into heat. And the amount of energy that's being absorbed and converted into heat, again, that's the imaginary part of this complex response function. Okay. So, so in principle, we have another 10 minutes or so, but this actually already strikes me as sort of a fair amount of kind of somewhat formal material. So I think I was just going to end here and kind of invite you this. So this is now chapter 10 of the book, and kind of invite you to maybe look at this now that you sort of see where this is going. See if you can follow the manipulations in the book. And if you have questions about that, again, either just ask on Friday or shoot me an email. But I think for now, I was just going to end here. And if there aren't any more questions, actually, I can just stop the recording and then ask if you have other questions as well.